Hi guys, Audrey here. Okay, so we've learned a lot about spans, about linear dependence and independence, and we've learned how to describe spans. So we're going to do a few problems where we determine whether sets of vectors are dependent or independent, and then we use what we know to describe their spans. So the first set we have, S1, is the set 1, -3, 6, 2, 2, 4. So what I notice here is that we have three vectors in R2. 3 is bigger than 2. So we have a theorem that tells us that these vectors must therefore definitely be linearly dependent. Now remember, when we have three vectors, linearly dependent means that at least one of these is not representing a new unique direction. So when we think about this, well, we know that it only takes two vectors to span all of R2. That means that with those first two vectors, I can cover the whole space R2. So 2, 4 is clearly a place I'm going to be able to get to. I don't need it to get to all of the same spaces. So in other words, what we're saying is that the span of 1, -3, 6, 2, 2, 4 is equal to the span of 1, -3, 6, 2. Now, an important thing to notice here, one of the things that makes this true, is the fact that none of these vectors are scalar multiples. So none of them represent the same direction. They're all going in like different places. It's just that one of those directions isn't useful. I can make it using the other two. So what that means is the span here is all of R2. So when we think about it, just to like make sure that we understand this, we're saying that 1, -3 is one direction, that 6, 2 is a different direction. These directions have nothing to do with reality. I'm just showing two different directions. I can literally get to every single place on this paper using just those two directions, and they're different. However, if they were scalar multiples, then I might have this direction and this direction, and I definitely could not get to every place on the paper. So I've got these two different directions. I can get to every place on the paper. 2, 4 would just be adding this extra direction that's not important because it's still on the paper, and I can already get everywhere on the paper using those original two yellow vectors. So in other words, this set right here, that's my linearly dependent set, and this set right here is a linearly independent set. The span of the three of them is the same as the span of the two of them. It's all of R2. All right, let's look at another example. So we're going to look at S2 is the set -9, 2, 6, 7, 4, 0, 8, 0, 0. Now here, again, we just want to know, are they dependent or independent, and what is the span? We've got three vectors again, but this time we're in R3, so we can't make the same conclusion as before, but we can use the idea of a determinant. So we're going to check out the determinant of this matrix, -9, 2, 6, 7, 4, 0, 8, 0, 0. And I'm going to do cofactor expansion down the third column because that has a whole bunch of zeros. I could also do cofactor expansion across the third row. There are 2 zeros there as well. So first of all, I'm doing cofactor expansion here. That 8 is in plus minus plus in a plus place. So this is equal to 8 times the resulting 2 by 2. So we'll just look at our little plus minus matrix. That 8 was in the plus place. Okay, now a 2 by 2 is really straightforward. So this is equal to 8 times 0 minus 24. This does not equal 0. That's the only thing that's important to me. The determinant is not 0, which means that this would reduce to I. There would be a pivot in every single column. These are linearly independent. Linearly independent because determinant does not equal 0. And we remember that that is therefore reduces to I. Pivot in every column, which means they all represent independent, unique directions. We need all of them to get to all the same places. And if I need all of them, 3 vectors in R3, what does that span? It spans all of R3. So the span here is all of R3. All right, next question. So, how was I doing that? So number 3 here, we're going to look at S3 is equal to 3, -1, 9, 2. Here I have 2 vectors in R2. Actually doesn't matter what space they're in. When we have 2 vectors, we just have to check, are these things scalar multiples? And the answer is no, they're not. 3 times 3 gives me 9. -1 times 3 does not give me 2. So 2 vectors, not scalar multiples. That means they're linearly independent. And we already saw this on the other page. 2 independent vectors in R2 spans all of R2. Next question. S4 we have 4 vectors in R3 here. Oops, I forgot my little thing there. 4 vectors in R3. That's a 2, 2, 1. I'm going to rewrite it. 2, 2, 1. So I can immediately say that these are linearly dependent. They're linearly dependent because it is 4 vectors in R3, and 4 is bigger than 3. It only takes 3 vectors to span the whole space of R3. So if I've got 4, clearly one of those 4 vectors is useless. The question here, though, is there more than one vector that's useless? Am I actually covering the whole space? So to figure that out, we're going to row reduce this thing and counter pivot. So we have 1, 1, 0, 2, 2, 1, 2, 0, 1, 2, 2, 2. And I don't want this to get too long, so you should try this at home. Do your own row operations. I'm just going to write row ups here. Row ups. And that will get me to here. 1, 0, 0, 2, 1, 0, 2, 1, -2, 2, 2, 0. So what this means is, once we've seen this row reduction, I have 1 free variable. I've got 3 pivots. That 1 free variable is my useless vector. So in other words, I can say that the span of these vectors would not change if I got rid of that last vector. I don't need it. So this is equal to the span of 1, 1, 0, 2, 2, 1, 2, 0, 1. And notice the 3 vectors here, if I were to ignore that last column, if I were to cross the last column out, then I would have a pivot in every single column. So these 3 vectors are linearly independent. So the subset of 3 vectors is independent. Is linearly independent. Now, what is 3 vectors in R3 span? All of R3. So the span is all of R3. Okay, We're just going to do one more question before I finish this. Question 5. So we're going to let S5 equal to the set 2, 6, 9, 8, 3, 1, 2, 0, 0, 0, 0, 0. Okay, so the first thing is this set contains the 0 vector, and any set that contains the 0 vector is linearly dependent. Can I multiply 2, 6, 9, 8, 3 by 0 and get 0, 0, 0, 0, 0? Yes. So this is linearly dependent because it contains the 0 vector. The next question is, what does it span? Well, we're in R5 because there are 5 components in these vectors, 2, 6, 9, 8, 3, 5 components. We haven't really talked about what goes on in R5. That said, we've only got one direction here. That 0 vector is not giving me any direction. It's not giving me anything. So we've got one direction here. And if I can only walk in one direction forever, I'm walking along what shape? A line. So that means S5, the set of vectors, the span is a line in R5. And that's all for today. Bye, guys.